Okay, today we're going to talk about the general power rule for integrals and this thing called U substitution. So remember how we learned the power rules for derivatives and then we extended it to involve chain rule for power functions? Hopefully you still remember this, where if I take the derivative of a function raised to a power, you bring the power down, you reduce the power by 1, but you have this extra u prime, which is the derivative of the inside function. Well, if I reverse this process when integrating, we have what we call the general power rule for integrals. And this is the case where, yes, it's some function u to the power n, but we also see the derivative of u attached next to it. And if that's the case, the antiderivative of this is just equal to the function u raised to the power of n plus 1 divided by n plus 1 plus c. So in essence, it's the reverse chain rule because you're trying to get rid of that u prime. Where in the regular chain rule for derivatives, we added this hook on u prime. So hopefully I can give you this example here and I'll show you what this reverse chain rule is all about. So if I were asking you to differentiate this, I hope you remember it's just bringing down the 4. 1 plus 5x raised to the power 3. And because of chain rule, we have an extra factor of 5, the derivative from the inside. Right? Hook on factor. So now if I were to go backwards, if I integrate this, 5 bracket 1 plus 5x to the power 3, notice that this is my u, and the derivative of u would be 5, and that would be this. So you see how there's u and u prime? So if you can see that here, then I can just use the general power rule and just take u, which is 1 plus 5x, raise that to the power of 3 plus 1, which is 4, divide that by the new exponent 4, and then of course have a plus c. So as a note, you hook on the derivative of the inside of the power function, example number 1. That's this in green. So I had to unhook the derivative of the inside in example number 2. And that's this u prime here. So looking at a few more examples then, how would you integrate this? If I let this thing inside here be u, I'm really looking for where is u prime. Well, the derivative of 3x minus 1 is 3, but it's not there. So what you have to do is you have to add it in. So I'll put in a 3. But I can't just add in that 3. I have to balance it out by putting a 1/3 in front as well. So now, taking this entire piece, I can use the general reverse power rule, and the antiderivative here becomes 3x minus 1 to the power 11 over 11, and don't forget I still have that factor of 1/3 in front, and so if I simplify this, that's 1 over 33, 3x minus 1 to the power 11, and then plus c. By the way, I forgot this dx here. Okay. Let's try example number 4. So once again, you're looking at what could be u and what is u prime. Notice we have something with a square term and a cubic term. Always try to take the higher power as your u. So if I let this whole thing equal to u prime just happens to be 3t squared plus 2t. Oh, great. That's actually this. Perfect. So I have that u and u prime next to each other. So I can just quickly do the general power rule antiderivative. So I'll take my u function, I'll raise it to the power of 1 plus 1, which is 2, and I'll divide that by 2 and plus c. And there's your answer. Now you can always double check these by just taking your answer and taking the derivative. Don't forget to use chain rule, and you should get what we started with. Let's see example 5. What looks complicated here? If you said this 4x cubed plus 5, you will be correct. And if I did this on the side and said, what's u prime? U prime should be 12x squared. So the question is, do you see a 12x squared? And I don't see it. but I do see 6x squared. So if I were to multiply by an extra factor of 2, that will give me the 12. But I can't just arbitrarily do that because that changes the value of the expression. So I better put a 1/2 in front to balance it out. This is nice because now this entire part is my u prime. And so now I can go ahead and once again use the general power rule. 4x cubed minus 5. This used to be 4x cubed minus 5 to the power of negative 1/2. So now if I add 1 to the exponent, that would be positive 1/2. And I'm going to divide that by 1/2. And then notice the 1/2 divided by 1/2, those just divide out. And so I'm really left with 4x cubed minus 5 to the power of 1/2 plus c. Done. Let's take a look at example number 6. You may be thinking, hey, let that equal to u. So u prime would be 3y squared. I don't see 3y squared anywhere, so can I just plug it in like this and divide by that? And the answer is no. All the other examples were just constants. This is a function. You can't do that, because I still have to figure out a way to anti-differentiate this 1 over 3y squared, which I can't. So unfortunately for this one, you can't do it by general reverse power rule. You just need to expand this out and integrate or anti-differentiate term by term. So probably writing this as y to the power of 6 plus 2y cubed plus 1 all dy, and then anti-differentiating these things individually. 2 over 4 plus y plus c. You want to simplify that 2 over 4 to 1 over 2. I'm glad to do that for you as well. And there's your answer for 6. Alright, let's turn the page. So that reverse chain rule doesn't work for everything. So there is another method we can use, usually for more complicated integration problems, but I can show you later on that this method also works for the previous questions we just did. Once again, in this case, it's called u substitution. So the idea is let whatever that is complicated equal to u. And the goal here is to change everything into u's. So if you had x's, we want to replace them all with u's. So here is a procedure, but I think I'm going to show you an example, and then hopefully that example will then illustrate the procedure. So once again, the key thing is to make the substitutions. So for example number 7, you have to decide what equals to u. And it's usually something complicated underneath the square root or in a bracket. So hopefully you can see that in this case u should equal to x minus 1. Okay. Now you should then take the derivative. So the derivative of u would be du dx. And its derivative on the right hand side would just be the value 1. Now remember, our goal is to solve for dx so that we can replace everything with x in terms of u. So I'm going to multiply both sides here by dx, so I get du equal to dx. And notice what can happen now. My integral becomes the integral of x with a root, you guessed it, u, and my dx now is actually du. And remember how I said everything should be in terms of u? Well, unfortunately, it's not. At least not yet. But lo and behold, if I take this expression u equals x minus 1 and actually solve for x, you will see that I can actually take this piece of information and substitute it in here as well. So therefore, you get the following. The integral of u plus 1, and I'm going to rewrite the root u as u to the power of 1/2 du. Notice now everything is in terms of u. And then I can just expand this out. The integral of u times u to the 1/2, that's u to the 3/2, plus 1 times u to the 1/2, that's u to the 1/2 du. And then now I can just use the regular anti-differentiation techniques by taking the antiderivative of u to the 3/2, add 1 to the exponent would be 5/2, divide by 5/2, which is the same thing as multiplying by 2/5. Same thing here, u to the power 3/2, dividing by 3/2, same thing as multiplying by 2/3, and don't forget plus c. Now, if you left your answer like this, I'd be like, you're almost done. Step 7 of this process, yes, we've already done 7 steps, is to substitute it back. So remember, we started with x, so we better resubstitute it back. 2/5 x minus 1 to the power 5/2, plus 2/3 x minus 1 to the power 3/2, plus c. And now we're done. Okay. Next one, number 8. Same kind of deal. So why don't I let you try this out first, okay? And then come back and look at my answer, please. Okay, so once again, u is the stuff in the square root. The derivative in this case is 2. I can rewrite this as du equals to 2 dx. Or more importantly, maybe I'll solve for dx, so that would be du divided by 2. And so now you can start replacing 2x minus 1 root u, and that dx is now du over 2. But once again, we need to solve for that x there. So taking this expression, hey, maybe in this case I actually just solve for 2x, because that equals to u minus 3. And that helps because I'm just replacing this 2x now. And that will become the integral of u minus 3 minus 1 over root u du, and I'll take that 1/2 and stick it outside. This is kind of nice because this is equal to 1/2 the integral of u minus 4 over root u du. And remember, the goal here is to rewrite this as a power, so u divided by root u is just root u, and this is 4 over root u du. I can once again rewrite these as exponents. And now you're set to anti-differentiate, which I will do right now. U to the 3/2, 2/3, minus 4, and then u to the positive 1/2, divide by 1/2, which is the same thing as multiply by 2. But because I have to distribute the 1/2 in, I'll just write this as 1/3 u to the 3/2. 1/2 times 4 divided by 1/2, well, that's, I think, just 4 u to the 1/2, and then don't forget plus c. And finally, yes, resubstitute it back. U again was, yeah, 2x plus 3, 2x plus 3, and now you're done. Did you get this answer? If you did, give yourself a pat on the back. So now you really have 3 strategies for doing this thing called integration or antiderivatives, term by term. The general power rule, which we did on the previous page, and then today on this page, use substitution. Now remember how I said that use substitution actually works for these questions too? So let me show you that, because if you don't really want to use general power rule, or if you thought it was kind of like odd or weird, then you can actually just use substitution for all these types of questions. So with the remaining space here, let me go back and do number 5 again. Okay, and I can show you how you can use u substitution. Okay, so 5 again. So I'll just quickly copy down the question. Integral of 6x squared over root 4x cubed minus 5 with a dx. Okay, so if we were to use u substitution, what would you let equal to u? If you said the stuff in the square root, bang on. Or it's stuff in this bracket. Now following this process, I'm going to find du dx, the derivative, which in this case is 12x squared. I'm going to actually solve for dx now. So du equals to 12x squared dx. And then solving for dx, that's the same thing as du over 12x squared. Now look what we can do. Let's make our substitutions. 6x squared still there. Root now u. Dx now becomes du over 12x squared. I got that from here, okay? Do you see what happens now with my x squareds? Goodbye, goodbye. Do you see what happens with the 6 and the 12? That combines with just the 1/2. And notice what you have now is this, which is exactly what you had before with example number 5. And if I were to rewrite this as a power, I get u to the negative 1/2. And then now if I actually take the antiderivative, this becomes u to the positive 1/2 divided by 1/2 plus c, which means it's just u to the 1/2 plus c. And then I can rewrite this or resubstitute it. U just happened to be 4x cubed plus, oops, not plus, minus 5 to the 1/2 plus c. And that is exactly the same answer you got on the previous page. So maybe a little bit longer, but maybe a little bit more straightforward as well. It's up to you, but you should know both methods. Alright, that's it. Try some problems.